Why light speed is the limit? There is a number at the heart of modern physics, 300,000 kilometers per second. It has been confirmed by countless experiments, embedded into the deepest equations science has ever produced, and accepted as one of the most fundamental constants in nature. For a long time, even the greatest minds believed this number was a property of light, something specific to photons and electromagnetic radiation. What Einstein and later Richard Feynman came to understand was something far more profound. That number has almost nothing to do with light. It is the speed at which cause and effect can travel through the universe. Once you grasp that distinction, everything changes. The story begins on a hillside near Florence in 1638. Galileo Galilei, already one of the most controversial thinkers in Europe, was trying to answer a question that seemed embarrassingly simple compared to the grand cosmological puzzles he usually worked on. How fast does light travel? His approach was elegant. He and an assistant would carry covered lanterns to separate hilltops. Galileo would uncover his light, sending a flash. The moment his assistant saw it, he would uncover his own. Galileo would measure the time between his signal and the returning flash, divide by the distance, and calculate the speed directly. The experiment failed completely. No matter how far apart they stood, the exchange appeared instantaneous. No delay. He repeated the test, increased the distance, worked with faster assistance. The result never changed. He concluded honestly that either light traveled at infinite speed, or it moved so quickly that no human-scale experiment could detect the difference. He suspected the latter. He had no way to confirm it. The fundamental problem was one of scale. Light travels fast enough to circle the entire Earth more than 7 times in a single second. The time it takes to cross the gap between two hilltops is measured in billionths of a second, far below anything instruments of the 1600s could detect. Galileo was asking exactly the right question in entirely the wrong place. To measure light's travel time, science would need the scale of the solar system itself. That opportunity arrived about 40 years later from an unexpected source, the orbital rhythm of one of Jupiter's moons. In the 1670s, a Danish astronomer named Ole Rømer was stationed at the Paris Observatory, assigned to observe Io, the innermost of Jupiter's large moons, and one of the most punctual objects in the known solar system. Io orbits Jupiter with impressive regularity, vanishing into its shadow and reappearing on a schedule so precise that astronomers were using it as a cosmic clock to help sailors calculate their longitude at sea. Rømer logged eclipse after eclipse with careful precision. For a while, everything aligned. Then, gradually, it didn't. A pattern emerged that resisted easy explanation. When Earth was on the side of its orbit closest to Jupiter, Io's eclipses arrived slightly early. When Earth moved to the far side, the eclipses ran late. The total discrepancy across Earth's full orbit accumulated to roughly 22 minutes. Most colleagues attributed this to measurement error. Rømer was not persuaded. The drift wasn't random. It tracked Earth's changing distance from Jupiter too consistently to be coincidence. In 1676, he proposed a different explanation entirely. The eclipses were happening on time. What was changing was how long the light from each eclipse took to reach Earth. When Earth was close to Jupiter, that light had less distance to cover. When Earth was farther away, the light needed more time to arrive. The delay wasn't a flaw in the data. It was a real measurement of something physical. Light had a finite speed. Using the 22-minute delay and the best available estimate of Earth's orbital diameter, Rømer calculated a speed of roughly 220,000 kilometers per second. The true value is closer to 300,000, and the discrepancy came from imprecise knowledge of Earth's orbital diameter. But the method was sound and the principle was correct. The implications, once accepted, were staggering. If light travels at a finite speed, every observation is delayed. The sun we see is the sun as it existed 8 minutes ago. Jupiter appears as it was roughly 40 minutes to an hour in the past. The nearest star beyond our own shows us light that left over 4 years ago. The Andromeda Galaxy, visible to the naked eye, appears as it was more than 2 million years ago. The universe we observe is not a single coherent snapshot of one moment. It is a layered composite, different objects seen at different points in their histories, all reaching our eyes simultaneously because their light happened to complete its journey at the same time. Every telescope is, in the most literal sense, a time machine. Looking outward through space and looking backward through time are not two different activities. They are the same activity. By the late 19th century, physics had constructed what seemed like a satisfying explanation for why light moved at the speed it did. Every wave phenomenon required a medium. Sound needed air. Water waves needed water. If light was a wave, something had to carry it through empty space. Physicists called this the luminiferous ether. The ether was a peculiar theoretical construct. It had to be extraordinarily rigid, more so than steel, because a wave's speed depends on a medium's stiffness, and light was faster than anything known. At the same time, it had to offer zero resistance to matter moving through it, since planets traveled through space without detectable drag. It filled the entire universe, permeated every object, and had never once been directly detected. It was a substance invented purely out of theoretical necessity. If the ether existed, though, it had a testable consequence. Earth moves around the sun at roughly 30 kilometers per second. If the ether was stationary, Earth had to be moving through it, creating an ether wind. Light traveling in the direction of Earth's motion should move slightly faster relative to Earth than light traveling perpendicular to it. The difference would be tiny, but late 19th century instruments were precise enough to detect it. In 1887, Albert Michelson and Edward Morley built a device to run the definitive test. An interferometer that split a single light beam into two perpendicular paths, bounced each off mirrors and recombined them. Any difference in speed between the two beams would shift the resulting interference pattern. The apparatus was mounted on a stone slab floating in liquid mercury to allow smooth rotation. They ran the experiment at different times of day and different seasons. Their device was sensitive enough to detect a shift 14 times smaller than the ether theory predicted. The shift they measured was effectively zero. No ether wind, no directional difference. Light moved at exactly the same speed regardless of which way the device was pointing. The most carefully designed experiment in the history of physics had returned a null result. Either the ether didn't exist, or it behaved in a way that made it completely undetectable, which raised the uncomfortable question of what purpose it served. Two theorists, Lorentz and Fitzgerald, proposed a mathematical rescue. Objects physically contract in the direction of their motion through the ether by exactly the right amount to cancel the expected effect. Lorentz showed that time itself ran differently for moving objects. The mathematics worked, but it required a troubling coincidence that nature would arrange two completely separate effects to cancel each other with perfect precision, specifically to hide the ether from every possible measurement. That kind of perfect concealment felt less like physics and more like a framework protecting itself from falsification. In 1905, Albert Einstein discarded the ether entirely and asked a more fundamental question. What is the minimum set of assumptions needed to make the laws of physics internally consistent? His answer rested on two principles. First, the laws of physics are identical for all observers moving at constant velocity. No experiment can determine whether you are in absolute motion or absolute rest. Second, the speed of light in vacuum is the same for all such observers, regardless of how fast they are moving or in what direction. The second principle was the radical one. In classical mechanics, speeds add. A ball thrown from a moving train travels at the combined speed relative to the ground. There was no obvious reason light should behave differently. And yet every experiment showed that it did. Einstein didn't try to explain this away. He accepted it as a fundamental feature of the universe and worked through the consequences. Those consequences were severe. If light speed is constant for all observers, time cannot flow at the same rate for everyone. A clock in motion relative to you runs more slowly, not because of any mechanical effect, but because time itself passes more slowly for moving objects. This is not a perceptual illusion. It is a genuine physical difference, confirmed by experiment. Two identical clocks started together will read differently after one takes a high-speed journey. Lengths also contract along the direction of motion. An object moving past you is shorter than it would be at rest, not because any compressive force acts on it, but because the geometry of space-time shortens distances in the direction of motion. Space and time, Einstein showed, are not two separate independent things. They are aspects of a single four-dimensional structure, space-time, and motion through space affects the rate of passage through time. Together, time dilation and length contraction ensure that every observer, regardless of velocity, always measures light at exactly the same speed. The universe adjusts distances and durations automatically to preserve that consistency across all reference frames. The ether was not hiding. It simply did not exist. Einstein's theory explained the mechanics with precision no previous framework could match, but still left the deepest question unanswered. It described how the speed of light was preserved through the warping of time and space, but not why the universe was built this way to begin with. Answering that required a fundamentally different kind of physics. By the time Richard Feynman came to prominence, the two greatest theories ever developed, Einstein's relativity and quantum mechanics, sat in direct contradiction. Relativity described a smooth, continuous universe where space-time bent and curved according to precise geometric rules. Quantum mechanics described something entirely different, a granular, probabilistic universe where particles had no definite positions or velocities until measured, where energy came in discrete packets, and where the future was not determined by the present. Both theories were experimentally confirmed in their respective domains, and yet they were mathematically incompatible. At the center of this tension sat the speed of light. Relativity required it to be absolutely fixed. Quantum mechanics required everything to fluctuate and resist certainty. How could any value be so rigidly enforced in a universe governed by quantum uncertainty? Feynman's breakthrough came from asking a deceptively simple question: what does a particle actually do between 2 points? Classical physics had a clean answer. A particle follows one definite path, the trajectory determined by the forces acting on it. Quantum mechanics had already undermined this picture, but didn't provide a fully satisfying replacement. The probabilities at the endpoints were well described. The journey itself remained conceptually murky. Feynman clarified it, and in doing so, rewrote the foundations of quantum theory. His insight, a particle moving from point A to point B does not take a single definite path. It takes every possible path simultaneously, not as a metaphor, literally. Every conceivable trajectory contributes to what actually happens. Straight paths and wildly curved ones. Smooth trajectories and violent zigzags. Routes that proceed directly between the 2 points, and routes that loop out to the edge of the observable universe before returning. All of them enter the calculation. This sounds like it should produce chaos. The answer lies in interference. Each path contributes what Feynman called a probability amplitude, a mathematical quantity with both a magnitude and a phase. These amplitudes don't add like ordinary numbers. They interfere like waves on water, some reinforcing each other, others canceling. What determines the phase of each path's amplitude? It depends on a quantity called the action, a measure of how the particle moves through space and time along that route. Paths close to the classical trajectory accumulate phases very similar to each other. When summed, they reinforce and dominate the final result. Paths that deviate wildly have phases that change rapidly and erratically from one to the next. When added together, they cancel almost perfectly. The more extreme the deviation, the more complete the cancellation. This is why classical physics works at everyday scales. The single trajectory Newton's equations predict is simply the path whose neighboring paths all agree with each other. Now apply this framework to the speed of light. For particles governed by relativity, the action that determines each path's phase contains the speed of light directly, as the conversion factor between distance and time within the geometry of space-time. When a path includes any segment where the particle moves faster than light, the contribution to the action becomes imaginary, shifting from a real number into the complex domain. As a result, the phase of that path's amplitude doesn't rotate at a finite rate. It oscillates infinitely fast. Infinitely fast oscillation means perfect, total cancellation. When all faster-than-light paths are combined in the sum, every single one cancels out completely, not approximately, not statistically, but with exact mathematical precision. Their contribution to physical reality is exactly zero. This is the critical point. These paths are not forbidden by some external rule. They exist within the mathematics. Feynman's framework includes them, calculates their amplitudes, and adds them to the sum. They simply contribute nothing. The universe cannot build any physical outcome from them because their interference pattern leaves nothing behind. Einstein showed that reaching light speed requires infinite energy, making the barrier unreachable from the outside. Feynman showed why the barrier exists at a deeper level. It is not a wall that stops you. It is a region where physics stops producing coherent answers. What Feynman uncovered was not a new restriction placed on the universe. It was a realization about what the universe is made of. Physical reality is not assembled from all possible histories. It is assembled from the histories that survive interference, the ones that can coexist without destroying each other. Faster-than-light histories cannot. They are mathematically present, but physically meaningless. The speed of light is not a rule the universe follows. It is a consequence of the only way quantum probability amplitudes and relativistic space-time geometry can coexist without collapsing into contradictions. To understand what the light-speed barrier feels like from the inside, strip away every practical obstacle and isolate the physics alone. Imagine a spacecraft with a perfect engine, unlimited fuel, perfect efficiency, no mechanical limitations. The only constraints are the ones written into space-time itself. The task: accelerate continuously until you reach the speed of light. In the early stages, everything behaves as expected. At 10% of light speed, you're moving at 30,000 kilometers per second, fast enough to cross Earth's entire diameter in under half a second. The engine delivers consistent thrust. Each unit of energy produces a corresponding increase in velocity. Then, somewhere around 50% of light speed, something begins to change. The engine output hasn't dropped. The thrust is identical to before. And yet the velocity gains have started shrinking. Each burst of energy produces a slightly smaller increase in speed. This is not friction. There is no force pushing back against the spacecraft. What is changing is the mathematical relationship between energy and velocity, governed by a factor Einstein's equations introduce called gamma. Gamma is defined by 1 divided by the square root of 1 minus the square of your velocity divided by the square of the speed of light. At low speeds, gamma barely affects anything. As velocity approaches light speed, gamma climbs without bound. At 90% of light speed, gamma is around 2.3, meaning you need more than twice the energy to achieve the same velocity gain. At 99%, gamma surpasses 7. At 99.9%, it climbs past 22. At 99.99%, it approaches 71. Each additional fraction of a percent multiplies the energy requirement by a larger factor than the step before. At exactly the speed of light, gamma becomes infinite. Not inconveniently large, but mathematically, precisely infinite. The energy required to push any object with mass to light speed is not bounded by any finite value. The barrier is not technological, it is mathematical. This plays out every day in real machines. At the Large Hadron Collider, protons are accelerated to approximately 99.9991% of light speed. Adding more energy at those velocities does not make them measurably faster. Instead, additional energy increases the proton's relativistic momentum, making them harder to deflect. The LHC's superconducting magnets operate at extreme field strengths, not to overcome friction, but to compensate for the relativistic momentum of particles at near-light velocities, a direct daily confirmation of gamma at work. Time dilation and length contraction add further dimensions to the barrier. As velocity increases, time aboard the spacecraft slows relative to the outside universe. This is confirmed by atomic clock experiments, GPS satellite corrections, and particle decay rates. A muon created in the upper atmosphere lives long enough to reach Earth's surface before decaying. Impossible given its known half-life unless its internal clock runs slower. As velocity approaches light speed, the slowing approaches a complete halt. At the limit, time would stop entirely for the moving object. An object with mass cannot exist in that state. Similarly, an object's length in the direction of travel approaches zero. As velocity approaches light speed, time stops, length collapses to zero, energy diverges to infinity. These are not three separate barriers stacked on top of each other. They are three expressions of the same underlying geometric reality. There is no continuous mathematical path leading from slower than light motion to light speed motion for anything with mass. The equations don't describe a difficult crossing. They describe a gap where no valid solution exists. Everything discussed so far describes the mechanics of approaching the barrier. But the deepest reason the barrier exists has nothing to do with energy or geometry. It has to do with the structure of cause and effect itself. In Einstein's universe, every pair of events falls into one of two categories. Some events are close enough in space and time that light could travel between them. These are called time-like or light-like separated events. For any such pair, every observer in the universe agrees on which happened first. The temporal order is absolute and cannot be reversed. Other events are separated by too much space and too little time for any signal at or below light speed to connect them. These are called space-like separated events. Because no causal connection exists between them, different observers moving at different velocities can genuinely disagree about their temporal order. One measures event A first, another measures event B first. A third sees them as simultaneous. None is making an error. The disagreement is a direct consequence of spacetime geometry. Under normal circumstances, this disagreement is harmless. Space-like separated events cannot influence each other anyway, but introduce faster-than-light signaling, and everything changes. A faster-than-light signal could connect space-like separated events, carrying information between locations with no causal relationship. And since those events have no fixed temporal order, such a signal will travel forward in time in some reference frames and backward in time in others. This follows directly from the mathematics of special relativity. Take any faster-than-light signal, in the sender's frame it travels forward in time. But there always exists another valid reference frame in which that signal arrives before it was sent. Faster-than-light communication in a relativistic universe is mathematically equivalent to backward-in-time communication for some observers, not in unusual edge cases, but in every case without exception. Once effect can precede cause, the logical structure of physics collapses. Consider, you send a faster-than-light message to a colleague on a distant space station. In your frame, you send it at noon and they receive it an hour later. In another valid frame, your colleague receives it before noon. They disagree with its content and immediately send a faster-than-light reply. That reply arrives at your location before you sent your original message. You now have your colleague's response before you made the decision to contact them. You could use that information to not send the message, eliminating the reply, eliminating your colleague's reaction, eliminating the reason you changed your decision. The causal chain has no consistent solution. This is the generic result of combining faster-than-light signaling with relative motion between observers. Any such mechanism can be used to construct scenarios of this type. Physicists examined every proposed escape route through the 20th century. Tachyons, hypothetical particles permanently above the light speed barrier, seemed mathematically symmetrical at first. But in some reference frames, a tachyon carries positive energy and moves forward in time. In others, the same tachyon carries negative energy and moves backward. No consistent time direction is possible. Any attempt to use them to send a message produces a causal paradox. Quantum tunneling appeared to offer a different loophole. When particles cross barriers they classically shouldn't be able to cross, the peak of the transmitted wave packet sometimes appears to arrive faster than light. But the peak is not where information resides. Information is carried by the leading edge, the earliest disturbance that could encode a signal. That leading edge never exceeds light speed. The Alcubierre warp drive, proposed in 1994, worked within general relativity by contracting space-time ahead of a vessel and expanding it behind. The ship remains stationary within its local bubble while the space-time region moves. But sustaining the bubble requires exotic matter with negative energy density in quantities exceeding the total mass energy of the observable universe. Beyond that, the occupants have no way to shut the drive down. Any signal they send toward the bubble boundary can never catch its superluminally moving front edge. Wormholes permit two distant regions of space-time to be connected by a tunnel. General relativity allows such solutions mathematically, but holding one open requires exotic matter with negative energy density, and without it the tunnel collapses instantly. Any traversable wormhole can also be converted into a time machine, reintroducing every causal paradox. Quantum entanglement is the most widely misunderstood case. Measuring one entangled particle instantly determines its distant partner's state. The correlation is real and confirmed experimentally, but entanglement does not transmit information. The outcome of each measurement is random. Neither observer can choose what result they get. The correlation only becomes apparent when both observers compare notes using ordinary communication, limited to light speed. This is not an empirical limitation that better technology might overcome. It is a mathematical theorem. The consistency of these failures points to the same underlying problem. In a universe where observers genuinely disagree about the temporal order of space-like separated events, faster-than-light signaling is backward-in-time signaling, and backward-in-time signaling makes it possible to construct events with no consistent causal solution. Where the effect eliminates its own cause, where information exists with no origin, where decisions are determined by their own consequences. A universe that permitted this would be one in which the concept of a physical law lost all meaning. A physical law describes what will happen given what has already happened. If the future can rewrite the past, that description becomes undefined. Physics as a predictive framework requires that causes precede effects, not as a convenience, but as its logical foundation. The speed of light enforces this foundation. It marks the exact boundary between events that can be causally connected and events that cannot. That boundary is set at precisely the threshold where consistent causality becomes impossible to maintain. The speed of light has spent most of this account looking like a barrier. But at larger scales, that framing inverts completely. The speed of light is not a ceiling placed on top of reality. It is the structure that reality is built from. Every event in space-time sits at the center of a geometric shape called a light cone. The past cone contains every event that could have influenced this moment. The future cone contains every event this moment could ever influence. Everything outside both cones is permanently disconnected, not unreachable with better technology, but geometrically severed. The speed of light defines the slope of those cones. It decides which events can be causes and which can be effects. It is not a rule written on top of that architecture. It is the architecture. Nowhere is this more concrete than near a black hole. When a sufficiently massive star exhausts its nuclear fuel, the collapse continues until space-time curves so steeply that an event horizon forms. At that surface, the escape velocity equals the speed of light exactly. Inside the horizon, space-time flows inward faster than light can travel outward. A photon emitted radially outward from just inside the boundary moves at full light speed relative to its local surroundings and still makes no progress toward the outside. The geometry of space-time, not any force, makes escape impossible. Inside a black hole, the singularity does not lie in a particular direction in space. It lies in the future. Every path through space-time inside the horizon, regardless of direction, leads toward it because it occupies the future of every possible trajectory. Escaping would require traveling backward in time. A black hole is not a prison with very strong walls. It is a region where the causal structure of space-time makes escape geometrically meaningless. The same geometry limits what we can observe across the universe as a whole. The universe is approximately 8 billion years old, yet the observable horizon lies roughly 46 billion light-years away. A consequence of cosmic expansion during the billions of years the light was in transit. Beyond that horizon lie regions from which no light has had time to reach us, and given the accelerating expansion of space, none ever will. Those regions are causally disconnected from us entirely. As expansion accelerates, more of the universe crosses this boundary permanently. This might sound like a limitation. At a deeper level, it is the reason the universe has structure at all. If information could propagate instantaneously, if every region were in immediate causal contact with every other, the cosmos would have equilibrated the moment it began. Every temperature difference, every density fluctuation would have smoothed out before developing into anything. Stars form because regions of higher density can collapse while surrounding regions remain less dense. A contrast that requires time and requires that distant regions not immediately share their conditions. The finite speed of causality gave the early universe the isolation needed to develop structure. Complexity requires locality. Locality requires a finite speed of causality. At the most fundamental level, the speed of light is not a property of light at all. It is the conversion factor between space and time. Space and time are not two separate independent dimensions. They are aspects of a single geometric structure, space-time. And the speed of light is the number that translates between them. 1 second of time is geometrically equivalent to approximately 300,000 kilometers of space. This is not a statement about photons. It is a statement about the geometry of the universe. Distance and duration are different ways of measuring the same underlying fabric. This is why physicists in certain theoretical contexts set the speed of light equal to 1 in their equations, not as a simplification, but as a recognition that space and time are fundamentally the same kind of thing expressed in units that happen to differ by a large numerical factor. The same conversion factor appears in EMC squared. Mass and energy are not merely related. They are the same quantity expressed in different units, with the speed of light squared as the exchange rate. The enormous energy values that equation predicts from modest masses exist because that conversion factor is so large. Feynman's framework showed that this limit is not enforced from outside the universe. It emerges from within. Particles explore every possible path through space-time simultaneously, and each path contributes a probability amplitude. Those amplitudes interfere. The ones that survive build into physical reality. Faster-than-light paths produce amplitudes that oscillate infinitely fast and cancel with exact precision. The universe does not block those paths. It simply cannot construct any physical outcome from them. They exist in the mathematics and contribute nothing to reality. Not that faster than light travel is expensive or technologically out of reach, but that the universe has no mechanism for constructing it into reality in the first place. The speed of light is the rate at which cause can reach effect. It is the tempo at which information propagates, the boundary between what can influence what. It governs black holes and particle accelerators, determines the size of the observable universe, and sets the pace at which that universe becomes less observable over time. It is the reason the past is fixed while the future remains open. The reason memory records what has happened rather than what will happen. The reason cause and effect are distinguishable at all. It is not the fastest thing in the universe. It is the reason the universe can exist as a coherent, structured reality in the first place.